Hi everybody, today we're talking about logical arguments. In mathematics, computer science, and formal reasoning, we often need to determine whether a claim follows logically from a set of assumptions. The purpose of the logical argument is to evaluate whether a conclusion is justified based on a given set of premises. Understanding this structure is foundational for proofs, which we'll be doing in the coming lessons. Formally, a logical argument consists of a finite set of statements called the premises. We put this together with a single statement called the conclusion. The key question in logic is not whether we agree with the conclusion, it's whether the conclusion follows from the premises. If the premises are true, the conclusion must be true for the argument to be valid. This means the logical structure is correct regardless of whether the premises are actually true in reality. Let's start with a simple example so we can build on structure and evaluation of arguments. I have P implies Q, P therefore Q. The P implies Q along with the P are the premises. The Q is the conclusion. The premises are joined together with the connector AND. Then they imply the conclusion. For this argument, we would have P implies Q and P implies Q. In our truth table, we will need columns for P, Q, P implies Q and P, then the whole argument P implies Q and P, therefore Q. We know that P starts true, true, false, false. Q will be true, false, true, false. For the implication, we know that true implies false is false. Everything else is true. That means true, true is true, true, false is false, false, true is true, and false, false is true. Our column is 1, 0, 1, 1. We're going to join this column with the first column of P. Because we're looking at AND, we know we need both of the items to be true for the connection to be true. True and true will be true, true and false will be false, false and true will be false, and false and true will be false again. We're going to take this column, put it together with our column for Q. The good news is 3 of our entries are false. False is immediately true when we're using implication, so I really only have to look at the first row. I have true implies true, which is true. Because I have all truths, we call that a tautology. Getting a tautology says the argument is valid. These premises imply this conclusion. So let's try a bigger example. We're going to test the validity of the following argument. We're given n is divisible by 6 if and only if n is divisible by 2 and 3. N is divisible by 2 or 3, therefore n is not divisible by 6. We'll start by assigning variables. We'll let P be the statement n is divisible by 6, Q will be the statement n is divisible by 2, R will be the statement n is divisible by 3. Let's label our argument. Our first premise can be written as P if and only if Q and R. The second premise is Q or R. Then our conclusion is not P. When we put our argument together, we always join the premise with and we use an implication over to the conclusion. That looks like P if and only if Q and R and Q or R implies not P. This is going to be a big truth table. We have our basic statements P, Q, and R. We need to put together Q and R, then we need to connect those to P with the double arrow. I'm going to label that with a 1 because it's our first premise. Our second premise is Q or R. I'm going to put a 2 on top of that. We need to put those 2 together with and. I'm going to call that 1 and 2. Then our conclusion is not P. Our final step puts the premise together with the conclusion, so I have 1 and 2 implies C. The first 3 columns we should know. P is true, 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 false, 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 false. Q is 2 truths, 2 false, 2 truths, 2 false. R is true, false all the way down. Our first connection is Q and R. And requires 2 true, and we see that twice in our columns. So I have a 1 in the first and fifth row and zeros everywhere else. Now I'm going to put that column together with our first column of P. we're using the biconditional, which says they have to have matching truth values, so either both true or both false. We can see that in the first row and in the last 3 rows. I put in a 1 in the first row and a 1 in the last 3 rows and zeros everywhere else. Next we move to Q or R. Or only needs 1 true, which we can see we have a lot of. So the first 3 rows are true, then I skip a row and the next 3 rows are true. The other 2 are false. Now that I have my 2 premises, I put them together with the connective of AND, which says they both have to be true. That happens in the first row, in the 6th row, and in the 7th. Those 3 get trues, everything else get false. My conclusion is not P, so instead of 4 trues and 4 falses, I have 4 falses and 4 trues. My last step is to put these 2 columns together using implies. I'll start with true implies false, which we know is false. You could stop right there and say we're not getting a tautology, so we don't think this argument is valid. Or you could complete the rest of the truth table, and in this case, the rest of the values are true. Because I have a mixture of true and false, we call this a contingency. This contingency says the argument is invalid. As you're doing the arguments, be patient with yourself. Note that there's a lot of room for mistakes, so make sure you're checking your work as you go along. It's easy to make little mistakes when you only are entering zeros and ones.